Hello everybody. In this video we're going to be going over some exponent stuff. Very detailed name here. Basically we're going to be going over some exponential rules, exponent laws, if you've seen it or heard it called that in the past. And also some stuff that's going to help with our next connection, which would be to exponential functions. And some of this stuff connects back to geometric sequences that we saw earlier this week. So some of the basics with exponents, and this is more or less a little bit of a review. We know our product rule. In other words, when we multiply variables with the same base, we can simplify this by adding their exponents. So let's add some numbers to this. If we're doing something like x squared times x to the fourth, the trick here is not to multiply and make it x to the eighth, but we're kind of grouping these together, hence why we add them to get x to the sixth. Okay, so that's our multiplication rule. We add exponents. Similarly, or in the same kind of wave of motion here, when we divide like variables, like bases, in this case we refer to x as our base. So I couldn't apply that first rule or this rule if I had like x and y. They would have to be the same base, either the same number or the same variable. I can subtract. That kind of goes hand in hand. So when I multiply, I add. When I'm dividing, I subtract. Now obviously with subtraction, the order matters. So we're subtracting the exponent in the numerator minus the exponent in the denominator. That's a sloppy N I have there. Okay, so something like x to the eighth divided by x to the third. You might panic and say 3 doesn't go into 8, but remember we're just simply subtracting. So that'd be x to the fifth. Okay, and then we have our, I kind of not accurately call it the double exponent rule. In other words, when we have something raised to a power, then we raise that to a second exponent. Okay, this is referred to more commonly as the power rule. I call it the double exponent. You could probably see why now. We see two exponents taking place. Okay, and I don't know why I made this the example. Let's use m and n again. Okay, what do we do here? This is when we're actually going to multiply. Okay, we don't multiply with the product rule. We only multiply with this double exponent or this power rule. And again, see a quick example of this taking place. This would be x to the 12th. Okay, so those are some of the basic rules. A quick one, it's not really a rule, but an important thing to know. Anything, emphasis, very heavy emphasis on anything, raised to the 0 power is not 0, it is 1. Okay, and then the proof around that, we can use an example like this. Okay, we know anything divided by itself is 1. We also know if we use our quotient rule, we can subtract here, which is x to the 0. Transitive property says two things equal to the same thing are equal to each other. So x to the 0 must be 1. We can use this for any case. Okay, so those are some of the basics. Those bullet points I would jot down, or you've had exposure to these in the past, but things that you're responsible for knowing at this point in algebra. What happens when you multiply like bases, when you divide, when you take a base and raise it to an additional exponent, that power rule, that double exponent, and obviously anything to the 0 power is 1. In the future, we'll take a look at negative exponents. That will have its own separate lesson, either in class or through another video. But these are some of the basic rules. So now what I want to take a quick look at, just using exponent rules. Obviously we use them, we've seen them already when we've done stuff like multiplying polynomials, box method, factoring, we see it a lot, but actually using it in a way that's not as direct. For example, we've seen this with sequences so far, and I'll make an example. Let's say, we start with something like 8. Okay, we multiply by another number, and we end up with 128. Okay, and this is just a quick, easy example, but the concept is very important. Okay, so we did this with geometric partial sequences. Okay, so we first want to find out what this big gap was. This does all connect back to exponents. So in other words, what did we multiply 8 by to get 128? Okay, through division of 128 divided by 8, we find that that product was 16. I know this is a very, very important concept, particularly with this example where it would work out nicely. If I wanted to find each step, it would not be this. This is incorrect. So I'm about to erase this in a second. Hopefully you don't shut off the video at this point and leave thinking this is true. It's not times 8 times 8. First of all, use some common sense. Okay, times 8 times 8 twice in a row would be the same as the product of 64. Okay, you could see how someone might make the mistake in saying 8. They're kind of confusing in arithmetic, or where we just have a sum. So like plus 16, yeah, that would be true. We could split up into plus 8 and plus 8 through division, right? 16 divided by 2 is the same as 8 plus 8. But with multiplication, it actually involves exponent rules. What we're really saying when we're trying to answer this, or exponents I should say, what we're really saying is some number, let's call that number x. Some number multiplied by itself twice is 16. Okay, that's really, and obviously we know the answer here, and you probably knew it the second I drew it out. But let's think about really what's going on behind the scenes here. Okay, that's really what we're saying, because this is going to help for harder examples. Some number times itself twice was 16. So how can you solve this? Okay, we can solve exponential equations when we have x raised to some power, and it's not just always going to be 2. It could be x to the 4th. In this case, we could take the square root. Okay, taking the square root of both sides would reveal the answer is times 4. However, and this is going to help for other cases, I like to think of it as raising to the, what's the relationship between 2 and 1/2 again? Those are called reciprocals. If we raise it to the reciprocal power, raising it to the 1/2 power is the same as taking the square root, but this can be applied to any type of power. So 3, I would raise it to the 1/3. If it says 5, I'd raise it to the 1/5. Using what we know about exponent rules, we multiply. 2 times 1/2 is just simply 1. So I get the x that I desire. And now 16 to the 1/2 power. That doesn't mean take half of 16. Okay, we could utilize our calculator here. We'd hit 16 caret 1/2. Or you hit 16 right above the division button. Type in 0.5 or 1/2 like this. And you get an answer of 4. Okay? And like I said, this is going to help with examples where we just can't simply apply a square root. For example, let's see one more here quickly. Let's say I wanted to do, let's say I have this. So I start at 5, I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and I end with 12, 15. I think that should work. Okay. So this gap here, again, we're going to do our division. 12, 15 divided by 5 is, long jump here, 243. Okay. So now this one's not as obvious. First of all, 243 isn't as common as 16. We have a lot of mini jumps here. So how many mini jumps do we have? We have 1, 2, 3, and 4, 5. So some number times itself 5 times here was 243. This is exactly what I meant in the last one. Now we can't do this in our head anymore. So really what we want to do is take the 5th root. And the last one we want to take the square root. Exponent-wise, taking the 5th root, we mentioned reciprocal powers. So what's the reciprocal of 5? 1/5. Okay, so I'm going to raise each side to the 1/5 power. I'm keeping it balanced. I'm doing the same thing on either side. X to the 5th raised to the 1/5 is just going to be x. Use our double exponent rule, or power rule. And 243, I'm going to need my calculator here, 243 raised to the 1/5 power. Hit the caret button for exponent, I get 3. So this ends up just being times 3 over and over again. Okay, you might have got that through guess and check, but this will help you with any example. We're going to see some where fractions might be involved, stuff that we can't guess. Okay, Another option, very quickly, if you don't like the exponent concept here, you can take a fifth root. You can access this on your calculator. Okay, it's a little tricky, which is why I prefer the exponents. You'd first have to type in the root that you want to take. So in this case, if we're taking the fifth root on a blank calculator screen, you hit 5. You then hit math. So you hit the math button right below alpha. You scroll down, I shouldn't say to the right. You scroll down to option 5. Coincidence here. So scroll down to option 5 and select, it says X. You see a little radical. In other words, we type that 5 in first because of the X. So that's telling us we're going to take the fifth root. And you could type in anything there. They have a cube root. Obviously, your calculator has a square root as an actual physical button. And cube root you see as option 4. But we could take any root using option 5. The variable radical there. It says X radical. Okay, so the fifth root. Then we type in 243 once we have the radical underneath. And we can get it that way. I think exponents are a little bit cleaner, a little bit more efficient. But you can actually have physical radicals on your calculator if you prefer those. Okay, so this was supposed to be a quick summary on exponents, but a little bit of a further connection into geometric sequences and actually using exponent rules. So this has been exponent stuff and more. Hopefully you found this beneficial. And if you have any further questions, please let me know either below in the Google form or in class when we return. Thank you for watching and have a wonderful day.